I was doing some thinking and just having some time to continue to improve my designs, and I came up with this idea that we should use the ATmega 2560 microcontroller instead of the ATmega 328P. This is for the Arduino Mega instead of the Arduino Uno or Nano. It's a bigger one. It has 100 pins on it. So like the Arduino ATmega 328P microcontroller has 8 pins per side. This has 25 pins per side. So it's got 16 analog input pins, and then like the rest of them, besides communication pins or whatever, there's like a ton of digital output pins. So I realized this could run a lot more motors. Now, I think we've discussed this before. I don't plan to use ESCs per se. So like usually you buy a motor and then you buy ESC for that motor, and then you drive the ESC from your microcontroller. We're skipping the ESC step. We're going to drive the MOSFETs that ESC would normally drive directly from our microcontroller. So it's going from microcontroller to MOSFETs, no ESC involved. And then each microcontroller, because we went with this bigger one, can handle like 60 MOSFETs. There's 6 MOSFETs per brushless DC motor. So that means we get around 10 brushless DC motors we can drive from the single one of these. Now I anticipate approximately like 300 motors in the robot. So if this can handle 10, we need 30 of these to run the whole robot, which is a lot better than what we were going to have to do before, since each ATmega 328P microcontroller could only handle like 3 motors, which means 6 times 3, 18 MOSFETs. This can handle a lot more MOSFETs. So it's a little bit bigger in size. The other one was like this. It's just like about double the size, but still very, very, very easy to fit in the robot, especially because it's not on a board. We're not going to have that large form factor board for the shoot. They're like this big for like the Arduino Mega. We're just having the little chip. That's all we need is the chip. And then from the chip, instead of having a board and a two-dimensional plane with all the components having to fit onto that plane, which highly constricts the total form factor requirements needed to be able to fit this onto the robot, instead we're using flat flex cable, so we can actually come around, we can bend the cable twice so that we can get every cable coming out in this direction, so our form factor can just be like this, just a stick, a flexible stick. So that's what I'm kind of leaning toward, a flexible stick. But I could also just wrap these around the robot like that, like wristbands, and just leave this that way. So we may not actually send them all in one direction. We might send them in 2 directions, or just leave them all like this. Now, the thread pitch on a ATmega 2560 microcontroller like this is 0.5 millimeter thread pitch, which means there's 0.5 millimeters from center to center on each of the terminal pins. And you're actually able to solder this right onto the flat flex. So this is the flat flex little pins you'd normally clasp into one of these little clamps that locks it into place on a circuit board, but we're actually soldering to it instead. And I was able to solder to it really cleanly using just hand soldering. Right here I had to sand away a little bit to access more metal to flow a little blob I had right here. So in order to prevent blobs, which is the main issue with this type of soldering, I realized we can just put with the tip of our X-Acto knife tiny bits of low temperature solder paste, which gives you your flux and your solder in perfect quantities. We were able to just brush it on like butter. Let me let this focus. Just like this, just kind of putting it in there, and then we dip a little bit more onto the tip of this thing, and then we just put it in there just like that. Dip a little more, put it in there just like that. Dip a little more, put it in there just like that. And I did this with the magnifier on, so I could see really, really zoomed in and do like really high quality work. Once you get used to the magnification, it improves your eye-hand coordination hugely, because you can focus so well and just do this tiny work so much easier. So once it's all on there, then I just took my soldering iron. So pretend this is the soldering iron. Oh no, I'll show you the soldering iron so that you guys know like what kind of tip I have and everything. This guy Voltar on YouTube, he does a lot of like retro game console mods, and he's fantastic at soldering. And so I watch his stuff, and I copied the type of tip he uses. So it's like this little needle nose tip. The camera doesn't want to focus right now. Oh, there we go. You see the little flat chisel shape to the tip? And yeah, it's really small. It's about like 2 millimeters wide. If you buy an assortment of tips on eBay or whatever, this will be one of them in it. So you just buy one of those assortments and pick this one out and install it. So anyways, I set my soldering iron at 703 degrees Fahrenheit. And with the solder already on there, I was able to just come in and just do like 1 or 2 pins at a time. I would just stick it in and pull, stick it and pull. So I'd do like 1 or 2 pins at a time, just one swipe, and then I would dip this thing into the mesh sponge of copper that I have with my soldering kit. I would just dip it like this, and then I'd rinse repeat. I'd do that again and again. That just would clear any excess solder from the tip, because too much solder is going to kill you on this. The whole key is to avoid blobs. That's like the entire key to the whole process. So then I would just go boom, and then I'd jab it in that copper mesh again, and then I just go boom. And I just kept doing that, like drag soldering 2 pins at a time. And since the heat vaporizes or like liquefies the solder paste instantly on contact, so you just move deliberately at a certain pace like this. But I notice if I just keep going down the whole thing, the solder would build up on the tip of this, and eventually I get like, by around here, if I started from here, by around here I would get some blobs, or it's not called blobs, what's it called? Where it like joins 2 pins together. Bridges. Yeah, you want to avoid bridges or blobs. So you just clean it after each one, and then just do 2 at a time. 1 or 2 at a time, just one swipe. You just get it in that crotch where the legs meet the flat flex. You just jab it in there and then pull back. Jab it in, pull back. And so I just do 1 jab and pull back at a time, and then clean my tip again. That's how serious I am about not getting any blobs. Now other people, they could load on a ton of no clean flux and like drag solder it and stuff, but they're not worried about heat at all. I am. See, this flat flex cable is not Kapton tape based like the flexible circuit board method you can do if you make your own circuit board using flexible circuit boards. It's based on actual like PVC plastic, I believe, and so that plastic melts pretty quickly. And so you have to get your soldering iron in there and out of there quickly so that this doesn't melt and start to seethe through and coat your pins with plastic. And actually I do have that happen a little bit, so I do have to like scrape away with the X-Acto knife any type of plastic that managed to like squeeze through. But the quicker I'm getting at just getting in and getting out, the less plastic issues I'm having. But I still scrape at it just to make it shiny and test it and like get a good look at everything. I'd smooth it out a little bit with my X-Acto knife just to kind of clean it. And I use like 100% isopropyl alcohol wipes, the Curad brand. I use those. They're individually sealed. $4 for a 100 pack. Just to wipe away when I'm done, to clear off the quote-unquote no clean flux or whatever. You still want to clean it, actually. So I clear off all the flux, and then I put on like the 15x or whatever little inspection jeweler's loop thing on my visor, and I'm able to get like a microscopic zoom, even more so than the normal one I'm working under, which is like 7x zoom, I think. And I'm able to see like really closely to see if there's any short circuits or anything. And these all look totally clean on very close inspection. So I feel like these are pretty clean. Even on the camera right now, they look pretty good. So once you have this all done, oh, by the way, also another tip is the way I'm showing you how I'm holding it with my thumb, I got these taped down. I can tape down the board when I only have like one thing with the board, but once you have all four, it gets easier. You tape everything down, you hold it on this proto board, and this is how I was soldering it, actually just holding it in the air like this. With my left hand holding everything in place. This thumb pins down pressure on the pins against the flat flex, so it holds the flat flex and the pins in perfect alignment. And then I was able to just hand solder them one at a time like this. And this is better than like working on a table because you can like be sitting in your chair, lounging and comfortable, like leaning back. Right now I'm sitting up, but I sat back, got real comfortable, and was able to just carefully do one at a time. And it actually, like once you get the hang of it, it's actually not too hard at all. Um, and so yeah. Um, okay, so also if you want to make like I messed up one time on a lot of these, I was able to like melt it off and pull it off, and then I cut off the bad section of flat flex, and I wanted to create a new lineup of exposed wire on the top. And in order to do that, to create your own exposed wire on these, I use a nail file, and I just rub over and over and over, and you can do that going the whole way through. But you just rub and rub and rub and rub until you see some little specks of shiny metal poking through it at spots. And that tells you that the plastic layer is extremely thin everywhere uniformly, if you're using uniform pressure everywhere and spending equal amount of time everywhere. So then I finish up with just going through with this and scraping with my X-Acto knife, scraping away that little thin veneer and exposing the rest of the metal. It's just a little quicker. Um, but everything is super gentle, super tactful, because you can easily cut right through the metal or sand right through the metal if you're just being too rough. So this pink nail file is perfect for me to do that, and I'm able to expose new copper. And now, like right here, you'll see this is not exposed metal at all. So how am I going to solder onto these pins? So basically, I'll be able to like sand away and then scrape away to expose metal, and then be able to solder stuff to the metal. Now, the next thing is, how do you like split these up? The whole point of this is to make these pins easier to access, where it's not all jumbled up together, because they're so close together, it's like a nightmare, right? You want to spread them out, kind of like those IC adapter boards, like make everything 1 inch or 1 millimeter separation through hole, um, or like Arduino's header pins are all spread out, easy to plug jumpers into. For that, you can just cut with scissors like this, straight titanium Westcott up embroidery scissors. I use 4 inch. I'm able to just really carefully under magnification cut along this and make perfect cuts between the two. So like um, each trace inside here, you can actually see it if you look closely. You can see little lines of separation. You need to cut between the two, like separating them. Um, and you can actually follow that under zoom. You can actually cut these lengthwise to separate them. So I can separate each and every one of these 25 into like little hairs. And then once you have the hair and you separate it all, you're dealing with like basically a wire by itself, and it's no longer joined to the pack. So then you can actually use that to solder it onto components. So I'd be soldering onto things with just one wire onto a component or whatever, and it'd be separate from the microcontroller. So we can add components out here. Or, you know, you can cut individual hairs shorter or longer, just kind of spread out the distribution of the components so they're not all like jammed at the very end of it. Um, and you can also add extensions onto here too if you want to make more components out this way or whatever. By you sand and separate these, and then you use a little bit more flat flex and you can join it to make like couplings. You can solder metal to metal, maybe overlap a little bit, and then do the same drag soldering we did here to join to make extensions. Now, the other thing is, since this is really fine stuff and we're not having like a hard, rigid surface to give kind of mechanical stability to it, if we're soldering in space like that, in order to secure and protect that joint that we make, we're going to use epoxy putty. And I'm kind of leaning toward this stuff I bought on Temu, Temu.com. Um, it's called steel epoxy adhesive. It cures in like 5 minutes, and it's just really nice stuff. You could use any type of 5 minute epoxy. I think would be good. Um, Maybe before you put that, just in case if that's conductive, you should like use conformal coating over it to protect it electrically and separate it from that. Or you could use UV cure solder mask to protect the actual solder joint and then go over the joint with the epoxy. And that's basically what they do inside ICs. Inside ICs is tons of little delicate circuitry, and they just coat all the circuitry with epoxy. This is epoxy or plastic that just protects everything, and only the little output pins do you see. So that same technique we can use for our joints and delicate circuitry to protect it. So all these joints I plan to coat in epoxy. So this will be coated like maybe up to here. Just coating everywhere I soldered on front and back. So this black part will just be extended out a little bit. So this will become a little bit bigger, but then all of these will be super mechanically secure. They'll never bust off or anything. And we can just bend them, fold them any which way, and not worry about any of these joints failing ever. And the same for any components you put on. I say you should always epoxy that joint to like make it super well secured, since it's not backed up by fiberglass board like this type of board. So this type of board I just selected as a board that is easy to hold with your left hand while you do your soldering work, or putting on your flux or the no clean flux, or putting on your solder paste, or using your alcohol to clean things, or sanding, or whatever you want to do. You can just do it over this board as a background, and because this board doesn't melt, it's fiberglass, you can solder on it, whereas something plastic would like melt. So this is a nice rigid surface just to work with, and you can tape to hold things down. So I didn't need helping hands at all because of this type of tactic. Just using my thumb and left hand is all the helping hands you need, and the tape on the board, and you're able to do all your solder work. So I'll be moving the board out to here when I want to like solder on components onto the tips of these. Also, by the way, I bought 50 pin wide 0.5 millimeter pitch flat flex, and these are 25 pins wide for each side of this microcontroller. So the 50 pin wide, the flat flex originally came in a bag like this wide. So I actually cut one of these edges, and you'd never know it because I can cut with like 0.1 millimeter accuracy just by having the high zoom and just cutting super carefully and following along. You can see little indications based on like, you can see where the underlying traces are inside here. You see that little light glare pattern? You see how there's like little separations where it's gray in between the little highlights? That is your hint when you're cutting to show you like, okay, that's where the separation is. I got to cut between those lights where the gray spots are. So that's how you can like, there's little clues like that when you study this carefully. You can see what's underlying the plastic, where the metal is inside this. And so you're able to just follow that. So I already proved that proof of concept that you can cut these lengthwise. So I'll probably cut the strings like all the way up to like right here. So these will all be separated. So they'll be flared out like that. And then you'll be able to work on them individually, labeling them. Also, once they're split up, or even before you split them up, it doesn't matter, you can brush on MG Chemicals Total Ground, which is like a carbon conductive paint that's made for RF shielding. You can shield each one of these individually so that we have no RF concerns. I learned a lot about RF related PCB board layout and ways to prevent your electronics from transmitting or receiving electrical signals and creating interference for local electrical devices. I read a lot about it, took a lot of notes on it. I understand a lot of it, but I'm not an expert on it, and it's a very complex field. Like words like electrical capacitance and inductive capacitance, and there's like all these crazy words you read and you have to think about and conceptualize. and kind of understanding the principles of it. It's challenging to me to wrap my head around all of that, and I feel like maybe nobody fully understands it, but maybe some people do, relatively speaking, fully understand it. I don't know how you describe that, but a lot of electricity I feel like has some mystery to it. Um, but anyways, by RF shielding everything and then grounding each one of the shields with like a little tiny ground wire, and then painting that on with the shield, everything can be grounded and shielded. Every single individual wire on here, for all of them. And I plan to do that with all of the electrical for the entire robot because we don't want crosstalk. Crosstalk is where you've got unintended electrical pulses hitting your wires and causing unpredictable behavior, flickering, like weird stuff with your motors, with your microcontroller shutting off and restarting itself because it's getting little pulses of electric that you didn't intend. And so you want to avoid that by making sure everything's well shielded. So I'll be shielding everything. After I shield it, I might add an insulative barrier on top of that yet. So we'd be painting it twice, or electrical tape over that. I'm not sure. But you might be able to just shield it because having exposed ground, which is what that would be, grounded ground stuff, should be fine. Because like the whole chassis of a metal robot would be your ground plane. So every wire being the final layer being ground should be fine, as long as any type of signal wire is well insulated, then you're okay. So now one thing I have to be careful about is if I'm cutting these longitudinally and then painting it with ground, um, if there were some exposed wire, because I cut a little bit too close, because this is very fine cutting work, um, that would be shorting it to ground there. So I just realized that now as I'm just discussing this, I will have to paint every single one of these wires after I cut them with conformal coating or UV cure solder mask to electrically um, seal any little bit of exposed signal wire. And once that's sealed, then I paint on my RF coating to make sure no RF coating conductive paint gets onto any exposed wire because that would create a short circuit. Although the conductive paint doesn't conduct real well, so the short circuit would probably have very high resistance, and it probably wouldn't. Well, no, it might be conductive enough to like heat up the wire and over time like burn things up. So yeah, that might break your microcontroller. So you got to be careful with that. So I will be painting all these first with conformal coating or UV cure solder mask just to protect it all, and then RF coating it. And that's a price I'm willing to pay. That added complexity, that's perfectly fine. Um, the main thing is we want to shield everything. When you shield it, you don't have to be as concerned with perfect like circuit layout and design from the RF standpoint, which a lot of people were concerned with when they heard I'm going to be deadbugging everything. But basically, I mean, you're still dealing with the same circuitry you would be, except you don't have a fiberglass plane that you're working on with all of your traces being adhered to that. So it's a different technique than is the standard. And I believe I'm pioneering this type of method, but somebody else might take credit. I came up with this on my own, though. So flat flex I came up with, and also flexible circuit boards I came up with. As far as like having them, each trace be like able to be lifted and conformed to any shape in three-dimensional space with your components not on a flat plane. See, people do people do flexible circuit boards where all their traces are on that flexible circuit board and all their components are on it, so you can bend the circuit board. But nobody's thought of like having the traces be individually separated and able to go any which direction, like hair, with all the pieces in 3D space, not just conforming to a single 2D plane. Even if that plane can bend, you're still sticking to a single plane. I'm leaving that plane and working in three-dimensional space by having the circuits be able to be, like, instead of everything's flat, you can have it like hair, like they can intersect, crisscross, whatever, just freely flowing, so you can just tuck it in wherever you want into your robot and not have to worry about space concerns too much at all, because they'll just find room for themselves, these little hairs with components on them, and hopefully not wedge themselves into moving mechanical parts. So you still have to like be careful about where it all goes. And actually, I thought after we fold these all and have them all going in a single direction, I could put like a Mr. Freeze bag over it all, to like hold it all in some type of volumetric constraint, so that it can't just splay out anywhere and end up like wedged into a brushless DC motor output shaft area and like get ripped up and tangled up in that. So we don't want that to happen. So I might eventually put it all in a bag at the end or something, or rubber band it or something to keep it from just going too crazy and where each of these little hairs end up. Um, so yeah, the next thing I gotta wire this up to a working Arduino board with USB that will be used as an in-circuit programmer, and we'll upload a bootloader to this using that technique, and then we'll upload sketches to this. And once we start having the ability to upload sketches to this, then we'll be able to start connecting these up to MOSFETs and start testing motor control with it. So there's still a lot of work to do to get all that going, but I just wanted to give you guys the update on this cool flat flex cable technique and give you guys some ideas. This is basically deadbugging 2.0. Like it's like an improved deadbug technique. Although you could say it's not really deadbug because the chip is not upside down, it's not dip style, and I'm not soldering individual wires to it. I'm able to solder them all at once from flat flex, and the chip is facing downward. Deadbug means the legs are facing upward. These are not. But it's still the same principle, I feel, as deadbugging, because you're not using a circuit board. You're not making a board, but you're creating a circuit in three-dimensional space using wires. So it's kind of like still using that existing concept which preceded me. But I guess I'm just kind of taking that to just different directions than what you typically see. So I'm creating like a custom type of deadbugging style that most people have never done that I've seen. What else can I say? Also, for all the little components like diodes and MOSFETs, I'm going to try as much as I can to use SMD style to cut down on space cost savings. So we want to keep everything as miniaturized as possible. That's also why I went with this, because now you only need one 5-volt regulator to handle one of these, which replaces like 3 ATmega 328Ps, which would have required 3 5-volt regulators and 3 of everything else that's needed to support the microcontroller circuitry-wise. So I feel like this just condenses things down even more, and then you need fewer microcontrollers, which reduces complexity as far as the communications system between all the microcontrollers communicating amongst one another and amongst the main brain's PC and the chest of the robot. It just simplifies everything, because you don't need 100 microcontrollers now, you only need 30. So that helps out. The only downside to that is the 0.5 millimeter pitch is a little bit more of a pain in the butt to work with. But I found out, hey, I can handle it. And with even more practice, it's going to get easier and easier. And I already had success. So I'm not worried about it. But it does start to reach the limits of what can be done by hand soldering, I feel like. 0.5 millimeter pitch is starting to get ridiculous. And some people say they can't even do it. But if they had the right techniques, I feel like anybody could do it. As long as you have steady hands and good eye-hand coordination and good eyes and stuff, and you have the right magnification, the right tools, I think anybody can do it. But you have to be very strategic and very careful about your techniques. So it has to be well thought out and very deliberate motions and everything. And it's made even harder by the fact that this melts. Now you could make flat flex cables like this using what's called Pyrex flexible PCB blanks. So it comes with like a sheet of copper over the top, and then it's capped on tape as the next layer, and that's pretty much like the way the circuit board comes to you. And you can then use the same techniques you would use to make custom PCBs on RF or no on laminated circuit board PCBs blanks. What is the name for that? I don't remember off the top of my head. I'm sorry, but you know, basically the stuff you buy to make circuit boards, that's fiberglass, and it has the copper layer on the top. Okay, you print out with your laser printer your circuit, and then you transfer that ink to the thing, and then you use copper etchant solution to burn away everything but the ink, and then you use acetone or whatever to clear off the ink, and then you're left with your traces. Then you can add your components. That whole technique, you can use that on Pyrex, except you'll end up with a flexible board. So you can use that whole system and setup to create your own these things, you know, coming off the pins. And you could even create, you know, an actual 2D plane circuit that way as well if you wanted to. So I have that, I have those options available. But I just wanted to test the flat flex as an alternative because it's already made for you and it's already coated top and bottom, and it just seems like possibly a time saver. So that's why I went with this. But I could have just made basically, you know, all these little pads to perfectly fit this type of microcontroller, blah blah blah, use the etchant myself, etc. But I just avoided all that with the flat flex, which is already good to go. It's ready to go. Like, this is how it comes in the mail, already with your pins that you can just solder to the edge of the microcontroller, ready to go, and they're perfect. So might as well just do that, I feel. But the downside is this is melty stuff, so you can't have your soldering iron on there for very long, and you can't use drag soldering techniques the traditional way, which generates too much heat, which causes plastic to get all caught up in here and gums up everything and just ruins this whole thing. You have to just be very careful in and out, little jabs where you're not introducing too much heat and melting the underlying substrate that coats these little traces. So that's the downside, but if you use the right tactics and you do figure that out and you can avoid melting this too much, then I think you do save time this way, so I like this tactic. I figured maybe we'll do a video of me actually soldering this stuff at some point, but why do it now? Even though I had success, I'm still a beginner. I've literally just done this, you know. So, and one other, I did a ATmega 328p before I did this one, because I was like, you know what? I found this thing in my electronics kit when I was going through it, and I was like, man, that's a lot of pins. That's so much better than the 328p. It's got so many pins on it, but it costs more. And that was the issue. Like, the ATmega 328p you can get for like $2 per, and buy like a 10-pack. So that's like $20 for 10 of them. But this was like $13 a lot of places, or you couldn't even buy it. It's like hard to find. But I was like, you know what? I don't care. I'll pay more, whatever it takes. I want to have something with more pins, and it'll just be so much easier to have all these extra pins to work with. This will be able to control way more motors. It'll just be better for me. And so I went ahead and made the splurge, and I went shopping for this, and it turned out I was able to find this for like $4 a piece on Alibaba from some seller. They haven't shipped it yet, but I ordered 30 of them, which should be enough for the whole robot, for $125. And that's like a great deal compared to what I can find. And so basically $4 each for these. It's $2 for the ATmega 328p, but this has like 3 times the number of pins. So it's basically like 3 ATmega 328Ps in one. And so if each ATmega 328P is $2, and this is like 3 of those, that'd be $6 of value. But I bought this for $4. So it's actually cheaper than using ATmega 328Ps, and gives you way more pins. So it seems like a huge win-win. As long as you have the skill to deal with the 0.5mm pitch. The ATmega 328P has 0.8mm pitch, which is a lot easier to work with. Even though it's like, well, it's only 0.3 millimeters, but that adds up somehow. Yeah, 0.8 versus 0.5, it's somewhat significant, but Still, both are very doable in my opinion. So, yeah, I think that covers it. And I'll give you guys updates as I continue to make big progress with this. But I just had to show you guys because this is kind of groundbreaking, revolutionary stuff. And basically, we're making it possible to fit a lot of electronics into the robot in a very miniaturized way that that conforms to the extreme space limitations that we have. Where to the point where we don't have room for circuit boards. We have room for flexible circuits that operate in 3 dimensions and conform to tight, cramped, and curving surface areas, but we don't have room for traditional 2D plane circuit boards. Those planes just demand flat areas, but we're dealing with curves, conforming to bones and wrists, between the bone and the skin right here, how much space is there? Could you fit? You have to have curving circuit boards to be able to fit it into, like, arms and stuff. This is just better for the humanoid robot form factor. If I made a humanoid robot that was a Minecraft character shape and the arm was just like rectangular extrusions or whatever, then 2D plane circuit boards would fit great in that. But because I'm using organic designs, my circuitry needs to have organic form factors. And so that's why this is excellent. The final shape of this thing will be like the shape of a muscle, so it will fit great in a body. Alright boys, so that's my update. Peace out. Okay guys, one more thing I wanted to add is, based on the video title I wanted to give it, this does go in line with the idea of a flower circuit. So this would be the stamen, and then these would be flower petals, and then this will be up in the air, and then it'll have a stem, which is where all the wires will come from. Then it'll have a root system where it distributes across the robot. And then the flowers, just like a real flower, the petals can fold up. Like before a flower opens, the petals fold up, and they lower when it's when the flower like is getting ripe or whatever you want to call it. So it would fold up, and then you would wrap it up, protecting it after it's been folded up. Um, and then once it's like that, you can bend the whole thing down and flatten it, just like if you were to step on a flower in the grass. It wouldn't break the flower; it would just bend over flat on the grass, and then it would slowly rise back up. And so that's the way we'll be able to tuck this way when we're not working on it. We'll just be able to wrap it up and then fold it over and wrap it all up like in like a Ziploc bag, kind of Mr. Freeze style, like the little bag you eat a Mr. Freeze out of. That will be kind of how you'd wrap it up to put it away, so to speak, until the next time you want to work on the components inside that. And we went over the Deadbug flower circuit. I named that because I came up with it. Because it looks kind of like a flower in principle. I did a drawing, I did a video on this. This is me actually making that now. This is progress on that. So that's why I wanted to include the idea of a flower circuit in the title. You won't be able to Google that and find results because this is something I created out of need being the mother of invention. Just traditional circuits. It's um, like if I just say I'm going to have 300 brushless DC motors in the robot, and I'm going to put a brushless ESC in the torso of the robot, like James Breton did with his robot dog. And then from that ESC, you just have 3 wires going to each motor. You don't want high speed switching, high power bursts of electric traveling long distances from the torso out to the extremities of the body to reach all the motors throughout the body's extremities. That's going to introduce a lot of RF concerns and crosstalk concerns, which James Breton suffered with tremendously. He complained about it. It's going to mess up your sensors and communications, everything. Now, I am doing RF shielding on every single wire in my robot to try to eliminate that, but that may not be enough. I don't even know. I'm just assuming RF shielding is going to do huge wonders at preventing a lot of that issues with that. but it still goes against principles of proper circuit design layout to have high-speed switching, high-power stuff traveling long distances. You want the distance of that to be as short as possible. So having the ESCs right on top of the motors is important. Now, if you're going to have the motors inside an arm and you need ESCs to go to that motor as close to the motor as possible, where in an arm, if you've got the bones of an arm and then a motor on top of that, where are you going to fit these huge ESCs that are on a 2D plane and they're flat, and all the you just can't fit it like that. But you can fit it if you're using this type of flexible thing where you can fold it up and just like smash it flat and it can bend in any direction. You can just weave it in wherever it fits. You just make it work. And so this is something very special, something that is necessary. People that are designing circuit boards for a television set or a big screen TV in the 70s, they had these giant circuit boards with all through-hole dip components, and it's all gigantic. And they're not concerned about space or not having it on a flat plane. So that's just where the state of the art went, because everything was big. But now with cell phones, everything got miniaturized, but they still kept the flat form factor because a cell phone is shaped like a brick. What happens when you need it to be miniaturized and have a curving surface in multiple directions and potentially curving in multiple different ways, like curving this way and curving this way? You just need to have very flexible, very organic circuitry. And we've had a few videos covering this before, and I call it the Deadbug solder, or the Deadbug flower circuit style. Maybe taking out Deadbug from the name would make sense, but I feel like leaving that in the name makes a little bit of sense because it's kind of similar in theory. When people think of Deadbug, they think of wiring point to point with no circuit board involved. There's no board. It's just components and wires connecting the components, but where's the board? And so I feel like that concept fits because that's essentially the same concept, even though they usually don't have it very flexible. It's usually like stiff wire, and it usually involves turning a through-hole IC upside down, which looks like bug legs up in the air. And we're not turning a through-hole IC upside down. We're having it face down, and we're using mostly SMD components. So in some ways, it's a little different than some of the ideas people have with Deadbug. It's a different take on it. It's like Deadbug 2.0. But I just wanted to add that in there.